We're going to do another example, but we're going to change it up a little bit. For one thing, we're going to do an example where the cross sections are perpendicular to the y-axis instead of the x-axis, and second, we're going to change the shape of the cross sections. So in this example, the base is the region bounded by this line, y equals 4 minus 2x, the x-axis and the y-axis. It's the yellow region that you see. And the cross sections will be semicircles whose diameter lies across the region perpendicular to the y-axis. So what do I mean by that? So the cross sections are going to have a diameter that looks like that. They're going to lie in that direction. And then they're going to grow. Let me draw it in here. So here's a cross section. It's perpendicular to the y-axis. I've drawn on the bottom the x, y, and z axes because now we're talking about a solid in 3 dimensions. So I have x here, y here, and then there's z. What you can see is that the cross section is going to look like that, and it's perpendicular. It lies across the yellow region. It's perpendicular to the y-axis. Okay, so the first thing we need to do is figure out what is the area of this cross section. Let's write something in here. So area of one cross section. How do we find that? Well, the cross section of a semicircle looks like this, and it's half of a circle, so we know that the area is going to be not pi r squared, but pi over 2r squared, because it's just half a circle. Now, if this is the diameter, then the radius is going to be 1/2 of that. So we'll put it in radius like that. So if the area of a semicircle is equal to pi over 2r squared, then it's also equal to pi over 2 times d over 2, where d is the diameter, squared. Well, once we do all the simplification, we're going to get pi d squared over 8. So that's the area of, I'll just draw a picture of one semicircle like that. So the area of the cross section, we're going to get it by subtracting right minus left, because as you can see, this diameter that I've drawn in here, that is the length of that diameter is going to be the horizontal distance from that point to that point. So what we need to do is just as we did when we switched to doing area in the y direction, we're going to need to solve for x in terms of y. So let's do a little algebra. Okay, so now I've written the same curve, not the curve, the line, the same diagonal line is as x is a function of y instead of y as a function of x. So you can see is that the distance between these 2 points is simply going to be right minus left, which is 2 minus 1/2 y on the right, minus the x-axis, sorry, the y-axis is just x equals 0, so that gives us 2 minus 1/2 y. That's the diameter. So we can write finally the area of one cross section is equal to pi over 8 times the diameter squared, and that's the area of one cross section. So now we can write the volume of a single slab. Let me just draw that in here. What we want to do is draw slab as having sort of a thickness like this. Making it a little bit thick, and if you notice, it grows. Sorry, get rid of that. If you notice, the slab grows in the y direction. In other words, it's going to have a thickness not of dx, but of dy. So the volume of one slab is equal to pi over 8, 2 minus 1/2 y squared dy, where this is the thickness and this is the area. So now we have the volume of one cross-sectional slab, and we can simply integrate it from the lowest possible y value up to the highest possible y value. Oh, and by the way, I know this is review, but remember that since we're doing a dy integral, that means that that's why we have to put only y's in the expression. You can't have an expression involving x and then end the integral with dy. That's just not allowed. So anyway, let's go back to the lowest possible value of y and the highest possible value. This point here at the bottom of the yellow region is 0, 0, and this point up here, which we can solve by setting x equals by setting x equal to 0, is 0, 4. So low value of 0, high value of 4, that gives us an integral for the full volume of the solid is the integral from 0 to 4 of this expression for the area of one slab. And now I'm just going to zip through the algebra. And we see that the area of this very strangely defined solid is 2 pi over 3. We want to do a brief comprehension check, so I've put up a fairly simple diagram. The yellow region is the region bounded on top by the line y equals x squared. That's just, no, I'm sorry, the parabola y equals x squared. On the right by the line x equals 2, and on the bottom by the x-axis. Now, suppose that we want to form a solid where the cross sections are squares that lie vertically across the yellow region. In other words, they're perpendicular to the x-axis, and a side of the square spans the region vertically. So I'm going to ask you a couple of questions about that scenario. Okay, now we're going to change the scenario a little bit. So the solid is formed once again with square cross sections, but now the squares lie horizontally across the yellow region. In other words, they span the region horizontally from the purple parabola to the red vertical line. Now I'm going to ask you a couple of questions about that scenario. When solving problems that involve setting up integrals for volume, it's sometimes useful just to remember some of the areas of some basic geometric figures. We've seen so far squares and semicircles. I'm sure you all know the area of a square is just x squared, where x is the length of its side. A circle, of course, has an area of pi r squared. Or if you know the diameter of the circle, you can write, since r is just equal to 1/2 d, you can write that as pi times d over 2 squared. Semicircle is basically the same thing. Since it's just half a circle, its area is either pi over 2r squared or pi over 2 times half the diameter squared. Some more exotic shapes that you might see, not that triangles are that exotic, is sometimes you might see that the cross sections are isosceles right triangles, where the hypotenuse of the right triangle lies across the base perpendicular to some axis. So in that case, the area of such a triangle is x squared over 4, where x is the length of the hypotenuse. If you want to know why that's true, just recall that an isosceles right triangle is a 45, 45, 90 right triangle. So you've seen this in an earlier geometry class, that the length of each side is x over root 2. The length of each leg is x over root 2 if the hypotenuse is x. So since we can multiply the two legs of a right triangle to get the area, and multiply the two legs of a right triangle together, and then multiply by 1/2 to get the area of a right triangle. We'll see that this is just equal to 1/2 times x over root 2 squared, because the two legs of an isosceles right triangle are equal to each other. An equilateral right triangle, the area is x squared root 3 over 4. The way we would get that is we'd say that if it's equilateral, then each side is of length x. If I break this in half, this is going to be x over 2. So what you can see is that I've broken the equilateral triangle into two 30, 60, 90 right triangles. That makes the altitude here x root 3 over 2. So that just comes out to, okay, I'm simply going to find the area of two of these half triangles. So that comes out to the altitude times the base of one of them. So that's going to be x root 3 over 2 times x over 2, which comes out to x squared root 3 over 4. That gives you the area of the full equilateral triangle.